So first of all, I just want to make sure everybody's finding the assignments okay and the drop-off boxes or whatever you call them for the assignments. There are still some people I know who have been at lab that haven't turned in the first assignment yet. So, you need to turn them in. That's a small part of your grade. So does anyone have any questions here about doing that? Also with the assignments, you need to show the steps in your work. You need to show the equations that you're using on the unit stuff. A few people still weren't showing any equations or were showing equations but not having the units in their calculations. So be sure that you're showing steps. Like the solutions that I post for that stuff is meant to show sort of the level of detail that I need to see to give full credit. So if you didn't get 1 out of 1 on the assignment, if you look at your grades, the one for the assignment 1 is up now. Basically like if you did it with the right level of detail, you got 1 out of 1 on it, and that's it. If you didn't, for everyone who didn't, I think I left notes in the grades, so look for that. All right, and okay, if any questions come up on that stuff, please send me an email and we'll get it straightened out. It's way better to get this stuff straightened out right now than halfway through the semester. And we still have not done a lecture quiz. We'll do the first one next week. Okay. And I'll put that on D2L to remind you the day before, a couple days before or something. But what you need to do for the lecture quiz, remember, is just read back, skim back over your notes. I'm going to be asking questions about sort of the big ideas that I'm bringing up to make sure that you're thinking about this stuff, going back and thinking about it. All right. We covered a lot of new material in the recent lectures. We started getting into actual physics, calculating motion, velocity, acceleration, and position. Did anybody have any questions in the assignments that you'd like to see me do or talk through? Sometimes I know it's more helpful to see it done than to just look at a solution. Anybody have any questions about the assignment? Okay. Then what I'm going to do today is I just have a few problems related to the recent assignment. There are really 2 types of problems that we've done so far, since units and all that stuff. We have the ones where some kind of motion is described, and then you're given a 0 position, a positive direction, and a 0 time, and you have to draw a position versus time graph. Okay, so I'll do one of those. And then the other ones are related to the constant acceleration equations. So those are ones where, an object starts at this speed and goes this far with this acceleration, and what's its speed at the end, what's the position at the end, questions like that. So I have a couple of questions like that to do. Okay, so the first one is position versus time graphs. And so here's what we got going on. Let's say, so this is supposed to, what does a refrigerator look like? What kind of handle does a refrigerator have? Like a long one like this? Okay, so that's supposed to be a refrigerator. This is the kitchen. Excuse me. And then this is a chair in the living room. And then this is the car. Oh, I'm going to call this living room so I can use a different letter than car. And let's say the distances between these are 10 meters and 30 meters. Okay. And so we're just going to plot a position versus time graph of like a morning routine. So let's say that the person starts in the kitchen. Actually, let's say the person starts in the living room. Okay, person starts in the living room. Then it takes 10 seconds to go to the kitchen. "20 seconds to get back to the living room. Let's say spends 30 seconds just sitting in the chair. That's a nice relaxing 30 seconds. And then it takes 50 seconds to go from the living room to the car. So this is the motion, and no matter what you choose for your zero position, positive direction, and zero time, that motion doesn't change. You know, you doing the physics of something doesn't change what actually happens. But we're going to do this now with two sets of choices of those things. So first we'll do it with, let's say that the zero position is at the kitchen. The positive direction is to the right in my picture, so like toward the car. And the instant that we're going to call time equals 0 is when the person leaves the living room. So when this whole description starts, okay? It doesn't have to be then, but that's what we're going to do at this time. I mean, you could call time equals 0 an hour before the person gets up and starts walking. I know I was going to say something. Well, anyways, so the way to start these problems, I think, is to draw just a diagram of the motion. It's easier to picture if you sort of draw out what's going on. And so I'm going to start out by drawing the motion without including this stuff, okay? Without including this zero position, positive direction, and zero time. So first I'm going to just draw out exactly what happens. So let's say that this is the kitchen, this is the living room, and this is the car. And no matter what we choose for these zeros and positive direction and stuff, this distance doesn't change. That's 10 meters. And this distance doesn't change. That's 30 meters. And the other thing that doesn't change is what the person does. So the person starts in the living room, goes back to the kitchen, and this takes 10 seconds. And then from there goes back to the living room, and that takes 20 seconds, I think I said. Okay. And then the person just waits in the living room for 30 seconds. So that position stays the same. Okay. And then from there, the person goes to the car. And that takes 50 seconds. So this is like a diagram of what happens, whether there's someone doing the physics of it or not, whether there's someone trying to graph it out or not. It doesn't change whether this happens, right? Everybody, that diagram sort of makes sense to everybody? All right, I'm going to copy this. On your paper, you might not have this option, but did that do it or not? But I'm going to do it, copy this just to emphasize that we can use this same diagram for the next part of this problem too when I give a new set of zeros and that kind of stuff, okay? This stuff is what doesn't change. But for part A now, we have this diagram of what happened, but we can't put any numbers on anything yet until we make these choices, until we choose what location is going to be called 0, what direction is going to be called positive, and what instant is going to be called time equals 0. So now we can make these selections. The position equals 0. We're going to start by, so this first part of the problem, we're going to call the 0 the kitchen. Okay. And we're going to call the positive direction to the right. And our time equals 0 is going to be when this whole motion starts. So this is going to be 0 seconds. Okay, that instant there. And so now let's use this stuff to label all the other things that happen. So if the kitchen is our 0 position, we can now give numerical labels for the living room and the car. Okay, so for the living room, if you start at 0 and go 10 meters in the positive direction from 0, what's the position of the living room? This is going to be, so if you start at 0, go in the positive direction 10 meters, this is going to be 10 meters. Okay? And now if you start at 10 meters and go another 30 meters in the positive direction, this is going to be 40 meters. Okay? So anytime you're in the living room, your position is 10. Anytime you're at the car, your position is 40. And now we can do sort of a simpler thing with the times, with these instants that are represented by these dots on this timeline. If we start at 0 seconds, think of that as that's when we turn on the stopwatch. Now the stopwatch is running for all the rest of this. What does the stopwatch say when we get to the kitchen? 10, yep. What does the stopwatch say when we get to the living room? Yep, 10 plus 20 is 30. Now we wait in the kitchen for wait in the living room for 30 seconds. What does the stopwatch say when we finally get up to leave for the car? 60, yep. And then when we get to the car, 110, yep. And now that we have everything labeled, I'm going to write out coordinate pairs for all of these things, because that's what a position versus time graph is, a set of coordinate pairs of a time and a corresponding position. So time and position. Okay, at 0 seconds here, that first instant that's labeled 0, so our time is 0 seconds. What's the position of the person at that instant? 10, yep. So what you're going with is the numeric label on that position line, okay? So the person has traveled a distance of 0 meters, but that's not what we care about. What we care about is what location that person's at, okay? So this is positive 10. And then the next instant is 10 seconds. What's the position of the person at 10 seconds? 0, yep. And then the next one is at 30 seconds. What's the person's position at 30 seconds? 10, yep. And then the next one is 60 seconds. What's the person's position at 60 seconds? Still at 10. And then the last one is 110 seconds. What's the person's position? 40 meters, yep. Now we've done all the work. It's just a matter of plotting these points out on a position versus time graph. We're always going to have position on the vertical axis and time on the horizontal axis. And let's see, if this is 110 seconds, the other times we need are 60 is going to be about here, 30 is going to be here, 10 is going to be here, and the positions we care about are 0, 10, and 40. So there's 10 meters. And here's 40 meters. So the first instant has a time. So why is time always on the horizontal and position always on the vertical? There's actually like a mathematical reason for that. I mean, time, so it's not constant, but I think you're sort of thinking of the right thing. The idea is that as time marches along, we're thinking of position as a function of time. And if you remember plotting functions in college algebra, your function value is always on the vertical axis, and your independent variable is always on the horizontal. So we're treating like time just goes. We don't really have control of that, and the position is what's determined by time. Okay. So the first point is 0, 10. So that's here. That's the start of the graph. The second point is 10, 0, so here. Then 30, 10. Then 60, 10. And then 110, 40. And if this was a real motion, it would sort of be curved. You can just draw these as straight lines. I'm going to draw them as a little bit curved, but I don't care about that. Okay, so that's a position versus time graph of the motion. Speaking of velocity, so one of the video lectures was on velocity and acceleration. And we'll do a lot of this kind of stuff in lab. But can you tell from that graph, what's an interval where the person's velocity is negative? This is a hard question when you've only seen this stuff zip by your face once. Yep. Yes. Between 0 and 10 seconds, the velocity is negative. And the way you know that is the slope of the position versus time graph is the velocity. Okay, and so to see where the velocity is negative, you're looking for places where the slope is negative. Okay, so remember, this is a 0 slope, this is a positive slope, and this is a negative slope. So the only place on that graph where you have a negative velocity is between 0 and 10. Okay, there are two places where the velocity is positive, meaning the person is moving in the positive direction. What are those two intervals? 10 to 30 and 60 to 110. Yep. And then there's one interval where the person isn't moving, the velocity is 0. What's that one? 30 to 60. Yep. And you can see that because it's 0 slope. And then the acceleration has to do with the concavity of the graph. Really, the concavity of the graph only has to do with how I drew it. If you drew it with straight lines, there'd be no concavity. But the way I have it drawn, you can see this graph is concave up from a little after 0 to about 30 seconds. And then concave down, I guess, from a little before 30 seconds to about 30 seconds, and concave up again. We'll talk about that stuff in lab. But from these position versus time graphs, if they're drawn carefully, you can tell the velocity signs and the acceleration signs. Okay, so now part B. No. Okay. So now it's going to be the same motion, but we're just going to make different choices because whoever's analyzing this, you're just making choices about what you're calling 0, what you're calling 0 time. The 0 time is it's when you turn on your stopwatch. The 0 position and the positive direction are sort of like, well, you're measuring it by laying down a long tape measure, say, and that just is where do you lay the tape measure down and what direction is it facing, okay? So this time, let's say the 0 position, how do I write that before p equals 0? Is at the living room this time. This time the positive direction is going to be to the left. Toward the kitchen. And the time equals 0 instant. So let's say this person, you might not know exactly when this person's going to get up. You don't control them. So let's say the person actually starts their stopwatch 30 seconds before the person gets up to walk to the kitchen. Okay, so the time equals 0 instant is 30 seconds before the motion starts. One thing that we're always going to use, there's no mathematical reason that you couldn't have negative times. It wouldn't change anything about really any of the math, but we're just only going to use positive times. So you might say, let's call time equals 0 when a person gets back to the living room, and then you have all those negative times. We're just not going to do that in this class because people don't tend to do it. Okay. So that is the motion. Remember, so this is the stuff. I'm just using exactly what I used before because none of this stuff depends at all on the choices. Okay, this just depends on what the person in the living room does. So the distances are there, the intervals of time are there, and what rooms you go to at what time are there. And now we're going to label this according to these new choices of position equals 0, positive direction, and time equals 0. Okay, so the living room now is what we're calling position equals 0. And this time the positive direction is to the left, which means to the right is a negative direction. Okay. If you start at 0, the living room, and go 10 meters in the positive direction, what's the position at the kitchen? Yep, this is positive 10 meters. I'll write the positive just to be clear. And if you start at 0 and go 30 meters in the negative direction, what's the position of the car? Negative 30, yep. And now for the instance, so when the person leaves the living room, what's the time? What does the stopwatch say? 30 seconds. If the stopwatch says 30 seconds and 10 more seconds go by, what does it say at the kitchen? Yep. And what does it say when you get back to the living room? Yep. And what does it say when you get up from the living room? And what does it say when you get to the car? Yeah. And so now I'm just going to write that same table I did before with these new values. So the first instant is 30 seconds and 0 meters. The second instant is 40 seconds and positive 10 meters. The third instant is 60 seconds and 0 meters. The fourth instant is 90 seconds and 0 meters. And then the last instant is 140 seconds and negative 30 meters. And now again, this is just a matter of plotting out the points. This time we'll have some negative positions. So the times we care about are 140, 90, somewhere around here, 60, 40, and 30. And the positions we care about are 0, so that would be the x-axis, positive 10 meters, and negative 30 meters. So now we can plot the points. We have 30, 0, 40, 10, 60, 0, 90, 0, and 140, negative 30. So it looks something like that. And if you look at these two graphs, I mean, this is all that really, understanding how to do this is what matters, because this will help you understand when we go on to using constant acceleration equations and stuff, what's going on. But just notice for a second that this graph, there's some stuff that looks similar between these two graphs. They have sort of this bunched up curve at the beginning and this spread out curve going the other direction at the end. But some stuff looks different. So what's the same and what's different? First of all, notice that the second one is flipped compared to the first one. That first bump goes up compared to going down in the first one. Any ideas what made that happen? Yeah. Yes, exactly. And I think a hint at that is like when we talked about the directions of the velocities, the signs of the velocities. Notice on that first one, the walk from the living room to the kitchen had a negative velocity, and here it has a positive velocity. That's because we switched what direction we call positive and negative. The person's still going to the kitchen, it's just we used to call it negative and now we call it positive. Okay. The second thing that you notice is the graph is shifted up and down. The first graph started at 10 meters. The second graph started at 0. What causes that vertical shift? That's right, the change in the 0 position. And then the last thing is a horizontal shift. You know, this one started at 0 time. This one started at time equals 30 seconds. What caused that horizontal shift? Yeah, the time equals 0. But if you did the math on these two things and calculated, so let's say that this was really a careful, accurate graph of what the person did, and you calculated the slope at one point and figured out the velocity. In that first graph, if we're talking about some point between 0 and 10 seconds, that graph, that velocity would be like, say, -5 meters per second. That's too fast. -2 meters per second. Okay. And then at this one, at the same instant, even though it's at a different time and a different position and stuff, you'd calculate that the velocity was equal to +2 meters per second. The magnitudes would be the same. The signs would be opposite, but notice what those signs mean would be the same thing. In both cases, it would tell you the person is moving 2 meters per second in the direction from the living room toward the kitchen. Okay. Any questions about that problem? There are a handful of problems on the assignments that you'll have to do like that, and when we get to exams and weekly homework assignments, you're going to definitely have to do a couple of problems like that. Okay, so after the position versus time stuff, you had to watch lectures on the constant acceleration equations. And I'm not going to go through like a full lecture on this, but I'm just going to sort of summarize what it talked about. So there are three constant acceleration equations that you need to get used to using. You don't have to memorize these. They'll be given on exams and stuff, but you're going to need to get used to using them. The first one says PF is equal to PI plus VITF plus 1/2 A TF squared. The second one says VF is equal to VI plus ATF and the third one says 2A times the quantity PF minus PI is equal to VF squared minus VI squared. And the meanings of these subscripts, PI and VI are the position and velocity at the instant when time is equal to 0. And PF and VF are the position velocity at the instant time final. And acceleration doesn't have any subscript because the idea of this is it's constant acceleration. So the acceleration is the same at time equals 0 and time final and every time in between. Okay, so there's only one acceleration you have to worry about. And to use these equations, there's a set of 4 steps that I gave you. The first one is you have to make 4 choices. To do those position versus time graphs, you only had to make 3. This has those 3, and then one other. You have to choose an instant corresponding to time final. So you have to choose a physical location that you're going to call position equals 0. You have to choose a physical direction that corresponds to positive. And these two, by the way, are arbitrary. You can choose anything for these. You just have to choose them because once you choose them, you have to be consistent through the rest of the problem. Okay. The other two, if you don't choose them right, you can't do the problem. And that is the time equals 0 instant and the time final instant. And you choose these instants based on when you're given information and when you're looking for information. So I'll try to point that out as we do these example problems. The second step is you need to figure out what variables you know and what variables you want. And there's only 6 variables that occur in these equations. So the variables that you care about are time final, position initial, and position final. Sorry, let me do it in a order. Time final, acceleration, and then position initial, position final, and then velocity initial and velocity final. So those are the 6 variables, and you can just go through that list and ask yourself, do we know those? Do we want those? Okay. There'll be some you don't know and you don't care about. And so I just write this out in, here's the ones we know, here's the one we want for each problem. You can only calculate one variable that you want with each use of a constant acceleration equation, because that's just math. You can only calculate one unknown with one equation. Okay. Third, now you have to choose what equation is going to work for you. And what you're looking for is an equation that has the variable you're trying to find, because obviously you can't solve for a variable that's not in your equation. And everything else in that equation is known, okay? Because you can't use an equation to solve for something with more than one unknown. So you're trying to find an equation that has the wanted variable and every other variable in the equation is known. At the start of using these equations, you'll always be able to find one that satisfies this. Later on, sometimes you won't be able to, and there's a way out of that. So step 4, this is optional, or not, it's not optional, but it doesn't always happen. But if no equation works, then use an equation to solve for an intermediate variable. And that intermediate variable is almost always going to be time final or acceleration. And then go back to step 3. Then hopefully now that you've found another variable, there'll be one more variable that you know, and hopefully you can find an equation that works. Okay. And I would recommend, for now, as you're getting used to this stuff, just have this list out sitting in front of you and just go through these steps. And what you want to do is just build patterns where you just do the same thing every time. So until that's sort of ingrained and you do it automatically and you just find yourself not looking at the steps anymore, just keep that in front of you as you work through these problems. All right, let's do an example problem. So let's say there's a boat at rest at the dock, and it takes off from the dock, and it takes 45 seconds to reach a speed of 20 meters per second. Takes 45 seconds to reach 20 meters per second. And we want to calculate the acceleration and how far has the boat traveled when it gets to that speed in those 45 seconds. In this class, you won't ever be like racing against the clock to finish a test or anything. I mean, at least not on purpose. Hopefully you won't ever. And so you have time to think about things. And I would recommend it never is a bad idea to spend a little time just drawing a picture of what's going on. It just helps you get it in your brain. It also, I find it never hurts to read a problem over a couple of times. I think before you really can work on a problem, you need to get to the point where you could describe it out of order, you know? So like it takes 45 seconds for this boat to get to 20 meters per second. It started at rest. What's the acceleration? Whatever. Like imagine someone quizzing you on all these things. It needs to be in your brain before you really have a chance to do the math on it. So, okay, here's the dock. Rough water. Here's the boat. And it takes 45 seconds. And we can use this picture just like we did in the first example today to when we choose the zero position, positive direction, stuff like that. We can do that on here. All right, so the steps are, the first thing we have to do is choose zero position, positive direction, zero time, and time final. So first, position equals 0 and positive direction are arbitrary. You can do this problem no matter what your choices are. I would tend to see a problem like this and choose the dock to be the 0 position and the direction of motion to be the positive direction. But you don't have to do that. But so let's say P equals 0 is the dock. The positive direction is the direction of motion. And now the two time choices. Now these are the ones that you just have to get right, but the wording of the problem always tells you what your choices need to be. Anywhere we know information, we want that to be a choice, and anywhere we want information, we want that to be a choice. So our time equals 0 is going to be when the boat leaves the dock. You know, the instant the boat leaves the dock. And our time final is going to be the instant the boat reaches 20 meters per second. So let's think about how the wording of the problem tells us that these need to be our choices. What information do we know and or want when the boat leaves the dock? We know the initial velocity is 0. Yep, it's at rest. Okay, so that's going to be helpful. We also know that it's 45 seconds between that first instant and what's going to end up being our time final. So we can use that time. Yeah, what information do we have at the end when the boat reaches 20 meters per second? We know that elapsed time, you know, and we know the final velocity. Yep. So I'm going to put my 0 position here. My positive direction this way. And I didn't leave myself a lot of room here. But so this is a pretty simple motion compared to what we did in the first example. But we know that the amount of time between these two instants is 45 seconds. So if we call this our time equals 0, this instant has to be 45 seconds. Okay, so now let's think about, out of these variables, time final, acceleration, P initial, P final, V initial, and V final. Which ones do we know and which ones do we want? I'm just going to go through this list in order. Do we know time final? Yep. That's 45 seconds. Do we know acceleration? No, but that's what we're asked for in part A, so that's what we want. Do we know the initial position? Yeah, what's that? And notice that, so yeah, and the dock is our 0. Notice that anytime your P equals 0 is the object's position at time equals 0, what you've done is define that PI is equal to 0. That's just another wording of the same thing. Do we know P final? Nope. We're trying to find that in part B, but not yet. So I'll just leave that off. Do we know V initial? Yes. We know that the speed is 20 meters. No, initial we know it's at rest. So initial is 0. Okay, we also know V final. We know that the speed is 20 meters per second, but the velocity could be plus or minus 20 meters per second. Which one is it in this case? Plus, and how do you know that? Yep, because the velocity, you know, the thing is moving in its direction of motion, which we call positive. All right, so is there an equation now that has A in it and everything else in it is shown here? Yes. The second of these 3 equations, wow, that's way back. V final equals V initial plus ATF. Sometimes there'll be cases where you can use more than one equation. In that case, use the simpler one. If you can use that second equation, always use that. It's just less messing around. There's no squares. Okay, so the equation that we can use here is V final is equal to V initial plus A TF. And so plug these in, and you get 20 meters per second is equal to 0 plus A times 45 seconds. And you won't have to do this for the whole class, but for now, I want you to do all your calculations, keeping the units in. And so you can use a mathematical notation that's the same as when you were doing unit conversions. So I'm going to write this as 20 meters per second. And to get the A by itself, we want to divide both sides by 45 seconds. So 45 seconds down here. And this is equal to A. And if you do this right, and you don't make any mistakes with your units, the units that come out are the units of your answer. Okay? And so that's one way to find mistakes if you make them. Because if you're looking for an acceleration and you come out with units of meters, you know that that's not, something went wrong. Okay? But in this case, you can look at the units and see we're going to come out with meters per second squared, which is units of acceleration. So that's a good sign. And so acceleration comes out to be 20/45, which is 4/9 meters per second squared, or 0.4 repeating meters per second squared. You can do this as fractions or decimals. I don't care. I don't care how you round. One other thing, you should always, when you get your answer, look at it and see if there's anything about the signs that can tell you that yes, this is probably on the right track, or no, something went wrong. Does it make sense that we would get a positive acceleration? It does. And the way you know that is if an object is speeding up, the velocity and acceleration have to have the same sign. It can both be positive or both be negative, but they have to be the same sign. If it's slowing down, they have to have opposite signs. So in this case, we know that the boat's speeding up, and we know that our velocity was positive, so the acceleration also has to be positive. Any questions about part A? Okay, so for part B, we're trying to find how far the boat's traveled in those 45 seconds. So we're going to start out by making those same 4 choices. And if you have a problem where you're doing multiple steps and your time equals 0 and your time final instance, like the instance where you're looking for stuff and where you know stuff haven't changed, then you probably can just use the same 4 choices you used in the first part. The only time you really can't is when it says, okay, now figure out what this boat is doing 20 seconds later or something. Okay, then you have a new instant that you have to look at, and the old choices aren't going to work. But in this case, those same 4 choices are going to work because we're looking for something at the same instant we were looking for before. And if you have the same choices of position equals 0, positive direction, time equals 0, time final. Then everything you knew before, you still know. And whatever you figured out before, now you know. Okay? So we can just move all the stuff that we had for part A down to here, and now we also know the acceleration. So our time final is 45 seconds. Now we know the acceleration is 4/9 meters per second squared. Our P initial is 0. Our P final, we don't know. We're trying to find that. Our V initial is 0. Our V final is 20 meters per second. So now, is there an equation that has P final in it and everything else is known? And actually, there are two of them, I think, here. So you could use either the first equation or the third equation. I'm going to use the first one. So P final is equal to P initial plus VI TF plus 1/2 A TF squared. So plug in the values. PF is equal to PI is 0. VI is 0, so this whole term has to be 0. And then plus 1/2 times 4/9 meters per second squared times 45 seconds squared. And now, so I can do all the unit calculations, I'm going to write this as 1/2 times 4/9 with meters in the numerator, seconds times seconds in the denominator. And then I'm going to multiply by 45 seconds. And it's squared, so I'm going to do that again, multiply again by 45 seconds. What units should we get for the final position? Meters, yep. And you can see if you do the unit calculation cancellations that the only unit we have left is meters. So that gives us a little confidence that we're going in the right direction. And if you multiply this out, you get 5 times 45 divided by 2 is 2, can't do it, too dumb. Can someone divide that out for me?
450.
150?
400.
Oh, 450. And the units are meters. It came out positive. Does it make sense that our final position answer would be positive? Yeah, because our positive was the direction it's moving. Okay, is there anything else we can use to troubleshoot that? I don't think so. So that's about it. That's how to do those. Any questions about that? Okay, let me do one more quick one. I'll get you out before time's out. Listen, shut up for a second. I need to talk to you about free fall. So that's the next set of lectures that you're going to watch videos on is all about free fall. But I'm going to just do this sort of cooked up problem that's related to the lab we just did, because basically what you did in the lab last week was an experiment where you approximated the acceleration of an object in free fall. We just didn't take the last step to see what our estimate was. So let's see how we would do that now that we have these constant acceleration equations, given that gravity makes things accelerate constantly. Okay, so let's say that you have this pinball and it falls 2 meters. And the average time that you calculated, or you didn't calculate it, you measured it. The average measured time was 0.64 seconds. What's your estimated, what's your estimated acceleration of gravity in free fall? Well, this is a pretty simple diagram. This object just starts at a height of 2 meters and goes down a distance of 2 meters. So first we have to make our choices of zero position, positive direction, zero time, time final. I tend to always, and this is when you get to the free fall videos, you're going to see that this is what I recommend. So I'm going to just put my zero position at the lowest spot in the problem. So P equals 0 is going to be on the ground. And my positive direction is going to be up. You could do different ones than this and get the answers just the same way, but this, I'm just starting you to get in this habit that I think that it usually simplifies the calculations a little. And then our time equals 0 instant is going to be when it's released. And our time final is going to be the instant right before it hits the ground. It can't be after it hits the ground because it's not constant acceleration anymore. And so given that, if we label this diagram, nope, that's not it. Our 0 is down at the ground. Our positive is up, which means the position where the ball is released is 2 meters. And our time equals 0 is when it's released, so this is 0 time. And our time final is just before it hits the ground, so this is time final. And actually, we know what time final is. Time final is 0.64 seconds. Okay, so let's figure out what we know and what we want. Time final is 0.64. Acceleration is what we're trying to find. What's P initial? Yep, positive 2 meters. Do we know P final? 0. Do we know V initial? It's released from rest. So this is 0. Do we know V final? We don't. It's going to be some negative velocity. We could calculate that later if we wanted to for some reason, but for now we'll just leave it off. But this is why, one of the reasons it's important to recognize that our time final is right before it hits the ground, not right after it hits the ground. Because right after it hits the ground, the velocity is 0. And so that's sort of an easy mistake to make, is say, oh, V final, it hit the ground, it's 0. But we don't know that. It's right before it hits the ground. Is there an equation that works with these? I think it should be the first equation again. PF is equal to PI plus VITF plus 1/2 ATF squared. So plug these in, you get 0 is equal to 2 meters plus this term is 0 plus 1/2 A times 0.64 seconds squared. I'm going to subtract 2 meters from both sides, and then I'm going to multiply and divide stuff out to get the A by itself. So we have negative 2 meters in the numerator. First, I'll divide by both sides by 2, which is, divide both sides by 1/2, which is multiplying by 2. And then I'll divide both sides by 0.64 seconds, and I have to do it twice because it's squared. And that's equal to the acceleration. The units, we know we're expecting meters per second squared because it's acceleration, and that's what we have, so that's a good sign. And if you multiply and divide out these numbers, you get that A is equal to 9. Can someone divide that out? I think it was like 9.77 or something. Okay. Which is pretty close to the true value of acceleration of gravity. The true value on at sea level is about 9.81. And so that's a very simple experiment, but if you do it carefully, you can get in the ballpark of calculating the acceleration of gravity in free fall. What about the negative sign? That's the last thing I want to ask about. Does that make sense? Okay, our positive direction was up. Gravity accelerates things downwards, so it should be negative. And also you can think about it as this ball starts out at rest and is speeding up, down. So velocity and acceleration have to have the same sign, and they're both negative. Okay, have a good weekend. And we have lab again next week. Yep, and tonight sometime I'll put up a new lecture on free fall and some new problems.